Hi, my name is Isaac Gerg, and I am with the Penn State Applied Research Laboratory, and I'm presenting my work with my collaborator and PhD advisor, Vishal Manga, who is with the Penn State Electrical Engineering Department. I am presenting today on preliminary results on distribution shift performance of deep networks for synthetic aperture sonar classification. A brief outline of the talk today includes an introduction to the problem, our experimental setup, our results, and some concluding remarks for machine learning practitioners. So here I show a SAS image with a truncated cone-shaped object, which is an interesting object for SAS machine learning classifiers. I show the original image chip along with three additionally sonar-relevant transformations applied to it, mean and median filtering for despeckling. Below each chip, I show the score given by a trained classifier for this problem. We see that the filtering, although not affecting human interpretation of the image, results in degraded performance of the machine learning algorithm. In this presentation, we will call such image transformations which maintain image semantics to humans as semantically stable transforms. A human operator might be tempted not to use the given classifier because it returns poor results on objects which are clearly of interest despite this simple filtering. We believe we can explain some of these findings by examining the difference in human and convolutional neural networks, or CNN, perception models. Here we show several properties of human and CNN perception as determined by several recent sources cited at the bottom of the slide. We see that the majority of properties present in human perception are not present in convolutional neural networks. This disparity creates a trust gap between humans and machine as they perceive the world quite differently. We provide 4 contributions to the community through this work. 1. We note that CNNs are easily fooled by a class of distribution shifts which we call semantically stable transforms, which are often sonar-relevant transforms and do not change the image semantics as interpreted by a human operator. We show that just because a deep network does well on a standard test set, that does not necessarily mean that it does well on images that have had semantically stable transforms performed upon them. 2. Quadratic phase error, which is a common phase error to SAS imagery, that this results in wildly varying performance across deep networks. 3. Deep networks evaluating SAS imagery often rely on low-frequency image content, which is not the case for the human visual system, generally speaking. And 4. We show that performance on a synthetically generated test set varies widely across networks. Overall, good performance on a standard test set does not correlate to good performance on these aforementioned distribution shifts. These results may help practitioners understand why changes to a new system or simulation may necessitate complete retraining to accommodate this quote-unquote new data. To demonstrate how distribution shift affects CNN performance, we examined 7 different network architectures using 3 different training regimes for a total evaluation of 19 networks. We evaluate traditional deep networks like VGG and ResNet along with contemporary deep networks like ConvNext and EfficientNet. We evaluate the 7 networks over 3 training schemes as a means to elucidate the effect these schemes have on machine learning performance. All of the networks are trained for 500 epochs using the Atom Optimizer. The first scheme is called Random Weight Initialization, or RWI. In this scheme, we randomly initialize the weights using the procedure outlined in the network's paper. The second scheme is called ImageNet Pre-training Initialization, or IPI. Here we initialize the network to ImageNet trained weights. Finally, the third scheme is called ImageNet Pre-training Initialization with Warm-up Training, or IPI-WUT. This is similar to IPI, but we train each network using a fine-tuning procedure consisting of 3 stages. The first stage allows for the batch normalization filters to warm up for 100 epochs. The second stage trains only the last layer parameters of the network for 200 epochs. And finally, the third stage trains all the network parameters for the last 200 epochs. Here we show results for each training scheme for each network across several semantically stable transformations. The axis of the radar plots is AUC-ROC. Larger numbers are going to indicate better performance. The semantically stable transforms we evaluate are median 3x3 filtering, median 5x5 filtering, mean 2x2 filtering, and diagonal image translations of 1, 3, and 5 pixels. We can see that for many of the networks, good performance on the standard test set is not correlated with good performance on semantically stable transformations, despite human operators having little trouble classifying these images. To better show the relationship between standard test set performance and semantically stable transform performance, we present AUC ROC for the standard test set against the mean AUC ROC of the semantically stable transforms. Again, larger numbers indicate better results. We get a correlation coefficient of 0.62 between the standard test set performance and the semantically stable transformation performance. We plot a linear regression of these points as a solid line, and for comparison, we plot the line y equals x, indicating no difference in performance between the data sets. We can see that efficient net does well regardless of the training scheme, as shown by the red points along the dotted line. Next, we examine quadratic phase error, or QPE, as a function of machine learning performance. Here I show an example set of SAS images corrupted by quadratic phase error over a range of strengths from 0 to 20 radians. Recall that QPE is a common aberration present in SAS images. This figure shows machine learning performance as AUC ROC as a function of quadratic phase error strength. Again, larger numbers indicate better results. We see for some networks QPE actually improves performance, while for others it severely degrades performance. Additionally, some networks report consistent performance across range of QPE strengths like CovNext and EfficientNet. For a third experiment, we created a synthetic dataset using gradient domain blending and 3 targets in the test set, along with test set background tiles. The leftmost column shows the original SAS images containing 3 objects of interest. The 3 remaining rightmost columns show those objects embedded into new backgrounds from the test set using gradient domain blending. Note that we are able to preserve the object shadow and speckle field with this method. On this slide, we show the results of the synthetic dataset performance. Each plot shows accuracy as a function of threshold. For all plots, larger average values indicate better results. We can see that the overall ImageNet pre-training works better than without, and that the EfficientNet gives the best overall performance on this dataset. For our final experiment, we notch filter over several spatial frequency bands and measure machine learning performance. The top row here shows the notch filters used in the experiment, while the bottom row shows a resulting SAS image from the filtering. We can see that the largest change to the image content results from filtering of the 3 lowest notch filters, which appear on the left of this figure. Here we show AUC ROC as a function of notch filter location. We see that all the networks, regardless of training scheme, are heavily dependent on low frequency image content for correct classification. This seems interesting considering human operators often rely on localized high frequency content and features to identify objects. To conclude, we demonstrate 4 facets of machine learning performance on SAS imagery. 1. Convolutional neural networks are easily fooled by the application of semantically stable, sonar-relevant transforms of which humans have no trouble discerning. 2. A wide range of machine learning performance exists when quadratic phase error is present in the SAS image. 3. Machine learning performance on a synthetically generated dataset varies widely across the networks, but networks pre-training using ImageNet fare the best. 4. All convolutional neural networks evaluated heavily rely on low-frequency image content to make their prediction, and this is a noted difference between human operators and CNNs in terms of their perception. Overall, we think these results may help practitioners understand why changes to a sonar system or simulation sometimes necessitate complete retraining of a network to accommodate this quote-unquote new data. Thank you.